Thank you for joining us here in person and online. This is the last of this semester's Cosmic AI Hybrid Seminar Series. We have 3 speakers today. Our first speaker is fellow at NRAO, and he will talk to us about using neural networks to infer the light scattering properties of irregular.
Thank you all for being here. And you know, it's great to be here with people from Cosmic AI and people from a variety of backgrounds. I come from an astronomy background, and so here I really want to tell you what I think is a pretty successful case. Oops, setting up my timer real quick. Yeah, so I think it's a pretty successful case of an application of machine learning in astronomy. So, since I know the audience comes from various backgrounds, I think there is a need to maybe lay some groundwork into the context of the problem. And then later on, I'll demonstrate why I think machine learning turns out to be pretty useful. And it'll be a pretty good solution to the study of dust grains. So dust exists in various branches of astronomy, everywhere essentially. So from protoplanetary disks, that's where planets form, to supernova remnants, and of course the interstellar medium, the Milky Way, and of course dust in other galaxies. All right, and dust is really important because that's sort of in various environments. That's probably the key player in determining the heating and cooling, and also maybe the grain surface chemistry. I know that's a big interest in this area. And also, it just determines what we see, all right? So really inferring how big the grains are, how they're distributed, how many of them there are, what types of grains there are. And that's sort of really the fundamental challenge in the field. And so in this talk, though, I'll focus on just debris disks, right? And so I think many of you maybe have not heard of what debris disks are, but, let's say you go to a very dark site, you look up, and of course you can see the Milky Way galaxy. That's another example of dust that turns out to be pretty important. But also, if you look at something really faint, you can see this bright lane, all right? And it's aligned along with the other planets of our solar system, right? That's sort of our debris disk. Like we live inside that debris disk, and in fact, debris disks, they're just we have 2 debris disks actually, the asteroid belt and the Kuiper belt, right? And they're really just the leftover material from planet formation. All right. Nowadays we have great images of what debris disks look like. For example, from all the way from optical from HSC, J-T Herschel, and then all the way to millimeter with ALMA. Right. So with this really good observations, surely we should try to be able to understand the properties of dust. All right, so again, why should we care about debris disks? Well, just very quickly, we live in one, therefore we should probably try to learn more about it. Also, they could be indicators of planet-disk interactions. It's useful for people to infer planets. But I guess more importantly, it's in this we sort of expect the dust to undergo collisional grinding. So that might offer a unique window into the interiors of planets, right? Now, what's really sort of crucial about this context is that there's constant radiation pressure from the central star, all right? So it's constantly pushing our grains and leaving only the relatively larger grains in this environment. And whenever we want to understand light and its interactions with particles that are greater than the wavelength of light, that's where numerical simulations can be very costly, right? Okay, so this is the case I want to make. Incorporating the emission and scattering of irregular grains is difficult, but we can overcome it with neural networks. And so I'll further explain to you what exactly I mean there. This is typically where you're going to see a lot of concepts with just light scattering. All right, you have some incident light, it hits a particle, it'll scatter in some angle. All right, the scattering angle. I think we should all know. And also the scattered light, you could gather the amount of light as a function of angle. That gives you the total intensity the phase function essentially, but also light is polarized. So we also have to characterize its polarization, right? Now in the title, I had this this term, the Lorenz-Mie theory. All right, that's really just scattering of spheres, and that's about it. So here's sort of a diagram of what that means in the geometric optics regime. You have a sphere, it has some size. We can easily define what that size is. It's just the radius. It has some refractive index. In this case, it's n plus ik. It's a complex refractive index, and that's really all there is. Right? All that information is all you need to characterize the scattering of light. However, real grains are probably not spherical, right? For example, you've probably seen these images of the IDPs, the interplanetary dust particles, or if you look at, sample return missions from Ryugu or Bennu or other asteroids, it's all irregular. It's really hard to find any spherical grain, all right? That's sort of, I think we can make that broad statement. But it turns out that, then the question is, are spheres still a good approximation of real irregular grain? And here's one case where, well, I would argue that it's not a good approximation at all. So here is, a laboratory experiment. You can take these samples. I'm showing here, this is a Feldsart sample. Take these rocks, shine a laser on them, and then try to ask what is the polarization you get as a function of scattering angle, all right? So this is the plot you're seeing here. The black points are the data. That's the polarization you get. Now, because it's a laboratory experiment, you roughly know the size distribution. You roughly know what the composition is. That's all you need, really, to determine the scattering profile. And now if you apply that to spheres, you get polarization. That orange curve is the polarization you get, right? It's negative. Well, it's a difference in the sign of the polarization direction. But anyways, you can see that it's drastically different from the laboratory measurements, right? So, but if you, on the other hand, use proper scattering calculations of irregular grains. So this is really, this is a technique called discrete dipole approximation. But anyways, you get input whatever grain, shape, morphology you want, the refractive index, and you just calculate what it should be. Then you get the green curve right there, right? So, these two don't have to match. That's sort of an observed phenomenon right here, is that numerically, you can have grains that are, as long as they're irregular, they don't have to match. You can get pretty good approximations. But, this is really costly. For typically like these regimes we're talking about, it can easily take months of CPU time. These are irregular grains. You have to have an ensemble of irregular grains. And so it's easily months, all right? Now, where does that come into play in this grand scheme of things? I think everybody here probably knows about how to forward model resolved data, right? Usually we have data, you go through probably months of data calibration and imaging, and then you can assume some sort of disk structural model, the macroscopic model. You also still have to assume some sort of dust scattering model. And then you do maybe another few months of radiation transfer, do another few months of parameter search, and then write the paper. By that point, you've already spent maybe a year, all right? And if you're a grad student, you got to graduate. If you're a postdoc, you kind of have to find a job, right? So by that point, and then you run into the issue of, well, I've assumed spherical grains there, right? I've assumed that because it's easy. It takes only a few, less than a second, few milliseconds to do this calculation. But then you realize you get that referee report and saying, why assume spheres? Why not irregular grains? And then you're like, okay, because it's a whole field of its own, it would take another year to do a proper calculation of irregular grains. And so that's typically the bottleneck. Right? So really, this issue here it's a computational barrier that we're running into right now. Just to sort of solidify what I want to do now is, in fact, we could use a neural network to replace that piece right there. Instead of using grains, instead of using spheres, we could use a neural network to overcome that. All right. And so this is just to sort of emphasize what exactly I'm training here. Every astronomer knows the radiation transfer equation, right? This is just an equation. If you want to know how light is extincted, emitted, and then scattered, you need to know several coefficients, right? There are 8 coefficients in this particular problem that you need to know. And that entirely is dictated by whatever grain model you have, right? So for spheres, you can determine that. For irregular grains, those are the exact values you're trying to determine, right? Now here is, I think people have seen a neural network architecture in a variety of places by now. And what I'm doing is, very simple. You've got just a pretty dense connected layers. Your input parameters are, for scattering profiles is just 4, really. The size, some complex refractive index, and the scattering angle. And then you can output a cross-sectional property, right? A coefficient to that radiation transfer equation. Okay, so that's really about it for this neural network. And of course, how do we, after you have that neural network, there are plenty of hyperparameters you got to tune. But anyways, I can do optimization and all that. And I'll just jump straight to the results here. So here is a typical prediction plot, right? On the x-axis, if you want to assess how well your machine learning model is, you always look at this plot, right? On the x-axis, you have the true targets. These are your test data. Those are the value you should predict. And then the y-axis, that's their predicted values, right? And so here I've plotted many points here. I'm comparing 2 different cases. One is for the orange dots, that's what you would get if you took the test data, you take the training data and just do linear interpolation, right? And then you get this spread of points. Now the green dots is the case for the neural network model, right? A perfect model would lie on this dotted line, right? So you could sort of easily see by eye that the neural network is performing pretty well. And in fact, if you look at the numbers, typically people care about the RMSE. So we easily get 1 order of magnitude better. That's the root mean squared error between the prediction, of the model, right? So I think, we did a pretty good job in training the data. And also to sort of just visualize the scattering profiles better. This is the total intensity and also the linear polarization, right? Plotting here, I'm plotting 2 test, just visualization data, really. And so I guess the point I want to make here is that there's also evidence of pretty good extrapolation, right? The neural network actually could generalize pretty well. And why can I say that? Well, these 2 curves right here, the green and the orange, are sort of within the boundaries of the training data, right? This blue curve here, however, is sort of a size. And I just asked, what is the largest grain I can simulate? Just test it against the neural network, right? And that's the blue curve right here. The dotted line is the corresponding neural network model. So we can sort of identify as that this neural network was able to make predictions that sort of matched that really, long simulation. That simulation took about 6 years CPU time. The neural network takes about 10 milliseconds, all right? So if I had just used the neural network, I could have saved up to 10 billion times in speed up with, about a few % level accuracy. So of course, that's good and all. The neural network can, learn the test data pretty well. But what about reality? All right, so here's a benchmark against laboratory measurements. Again, the same laboratory data, and you just look at what you get with total intensity. Here, the black points are the data points again, and what you get with the polarization. So again, the green curve is the neural network model. It's doing pretty well, even for a laboratory benchmark. And that's not only true for total intensity and this linear polarization. What about the other cross-sectional quantities? Well, it's a pretty good performance overall, right? And so, if you were fine, I think that I can make the statement that if you were fine with fitting spheres, I think you would be, pretty happy to use this neural network. And a similar timescale, it's also a millisecond timescale. You aren't going to lose too much in the accuracy against real grains. And that's really sort of just the case I wanted to demonstrate. And here is just a few lessons I learned. So I think that dust scattering is a field that can greatly benefit from. One, it's generalizable to various environments. There's just so much dust everywhere. They're probably all not going to be spherical. And also you can scale to other wavelengths, right? The same model can be applied to GOC IR spectrum, or for example, ALMA millimeter total intensity or polarization. I didn't talk about scalability much, but feel free to ask that. And so this, this package is called Glitter, in which people can just download a few megabytes onto your laptop. You can get a pretty good performance for your like radiation transfer model. Also, I think another idea that I learned from this is that neural networks are probably will be a pretty good tool for rapid test of grain models, right? So I had to assume some irregular grain, but that's probably not true. There could be grains of other porosities. You could also have some sort of fractal aggregates, or even there could be ice coating. So there's a lot of physics in that grain itself, right? I just picked one model, but so I think if we can develop, I would encourage other people who are doing also similar dust scattering simulations that you could train a neural network and allow other people, like observers, etc., to use these models to better test the various physics of the grains itself. All right, I'm almost out of time. And also, I think, the broader idea, I think, this idea is not new. Dust scattering here is an example of an emulator, right? Just use a neural network to replace whatever physics. And I think the broader thing that one can consider is that if you only care about the macro physics of your whatever problem is, in this case, like dust structural parameters, etc., and if you have some sort of microphysics that determines some pesky coefficients involved, that there might be an opportunity for you to use some sort of emulator or to spend the time to do proper simulations to get rid of that peskiness and make it easy, right? So yeah, I think that's all I have for today. Thanks again, everyone.
Okay, thanks, Dan. We have time for a couple of questions. Questions in the room? Yeah.
So when you're talking about these dust grains and calculating the polarization, you talked about the level of non-sphericity, fine, but then you kind of showed like a really complex one. And you said the shape of it doesn't matter. Did I understand you correctly when you said that?
It seems that, yeah, that is something that's kind of observed, that, you can have various prescriptions of irregular grains, but it seems like as long as they are irregular enough, it's sort of, once it averages out, it's all roughly comparable.
Once it averages out over enough irregularity within a single grain is what you're saying?
No, over enough population of grains.
An ensemble of irregular grains. So then if that's the case, why do I require an emulator at all? Can't I just write down a curve that captures that output behavior?
Oh yeah, totally. You could also just do it out of the table, etc., right? Now, the issue is that, well, I guess not really issues of. So this is nothing. It's a pretty simple neural network, really. You'll have 4 parameters there, and so yes, if you have the computational capability to output a fairly dense table, depending on 4 parameters, then yeah, it's solely doable. However, you might need roughly gigabyte scale of data. Each data point is going to be time consuming. That's the true brute force way to get like 2% accuracy and interpolation. I can do the same thing with a neural network, but with just megabyte scale data, and that drastically shaves off a lot of computational power. So I think maybe that's one benefit of why this turned out to be useful.
That's helpful. Right.
Yeah. So really, the neural network is nothing fancy, but I think even a simple neural network like this, when placed in the right context, it could be something pretty powerful.
Okay. Well, thanks, Daniel, very much.
Yeah, thank you.